Welcome to this week's edition of Adventures in Sensing, brought to you by the Responsive Environments Group at the MIT Media Lab. Um, last couple weeks, we took sensors out into space. So looking at really interesting missions and different kinds of sensor platforms that would enable them, really pushing them into some extremes there. Here we're going to put them into a very interesting part of the Earth, but again, look out into space in a different way, I guess, in some sense. We're going to Antarctica, and it's a really wonderful place to detect things. Certainly, you've got dry air, you got a view of the sky, but you also have the ice, and the ice itself is wonderful. I mean, it's undisturbed, not much going on down there. It collects stuff over time. We'll hear about it, but we know it's a great place to look for meteorites and things like that. But you can look at smaller scale stuff, and that tells you a lot about what's happening up above to fall in. And then you can put things into the ice, because the ice at certain wavelengths is clear, and it's like a huge medium for a physics detector. And we'll hear about neutrino detection with putting strings of phototubes and other sensors into the ice itself at pretty massive scale, all of which are just wonderful undertakings telling us a lot about the universe and what's going on in it. So it's an exciting time, exciting topic, and we've got some great speakers lined up. I'll let Juliana introduce them and start us off. Go ahead.
All right, thanks so much, Joe. So thanks again for joining us today on our adventure to Antarctica. And thanks in particular to our two guest speakers, Professor Brian Fields at UIUC and Professor Justin Vandenbroucke at the University of Wisconsin-Madison. So this series is called Adventures in Sensing, and I'm excited about our talks because physics and astrophysics experiments, which are some of the most precise sensors that humans have ever made, are also deployed in some of the most exotic places on Earth. And I think there's some real visceral appeal to this. So you'll find experiments on Hawaiian mountaintops, Chilean desert, deep in Japanese mines, beneath the Mediterranean Sea, on the space station, and indeed in Antarctica, which is the subject of today's talk. So Brian Fields is a professor at UIUC. He's an astrophysicist whose research focuses on the extreme environments of the Big Bang and exploding stars. He is best known for his work on the formation of the elements hydrogen, helium, and lithium in the first seconds to minutes after the Big Bang. And in his most recent work, Professor Fields has joined forces with astrobiologists and paleontologists to examine nearby supernova in the Earth's past. And then Justin Vandenbroucke is a professor at the Wisconsin Ice Cube Particle Astrophysics Center in the physics department and has a joint appointment in the astronomy department since 2013. During 2012 to 2013, he was a NASA Einstein Fellow at the Kavli Institute for Particle Astrophysics and Cosmology. And his group works on both data analysis and instrumentation development, including at the Ice Cube experiment. So I'll just add briefly that if you're joining us from outside of the Media Lab, either another MIT department or another university, please introduce yourselves in the chat. We'd love to know where folks are coming from. So each of our speakers will talk for about 20 or 25 minutes. We'll do a few questions after each talk, and then if our speakers can stick around a little bit, we'll do an open forum discussion just after the two talks. So with that, can kick it away.
All right. Well, thank you all for coming, and thank you, Juliana and Joe, for this for the invitation and the nice introduction. So so you can see my screen. Good. All right. So it's a great pleasure to have the chance to tell you about something I'm really excited about. And just as you've heard, we'll see how Antarctica is for me and for Justin an amazing witness to the most powerful events in the universe. And what I will be talking about is what happens when stars attack. And I'm not talking about ill-behaved Hollywood celebrities. I mean actual astrophysical explosions, in particular supernova explosions, and we'll see how they leave their traces in imperceptible microscopic dust in Antarctic snow. So the adventure part of this, how did I get involved in all of this? Well, how it started was I was just a graduate student, and I started to work on this problem thanks to the suggestion of my advisor and MIT alumnus. We thought about near-Earth supernovae and how you would detect them. And it was just an interesting theoretical exercise, which was sort of a hobby when I could spare some time from my doing respectable science, like making the elements in the early universe. But over time, it's become more and more interesting, as I hope you will see. So you'll see why it was a hobby to begin with, because it's kind of crazy, and then how it's become interesting enough that now it's really some exciting science, and it's certainly the most fun thing that I work on now. And so now I'm kind of like old Homer, who's a little bit stunned this has all worked out so well. So I have to say a lot of luck was important here, because you can see this trash can that's full of all the unsuccessful crazy ideas that I'm not giving a talk about. So this is the one crazy idea that actually paid off. All right, so here we go. So we're going to talk about supernova explosions near the Earth. So to make sure everyone's on the same page, not everybody's an astro person. So let's just review some of the basics of supernovae. All right. So the way you get a supernova is start with a massive star. So supernovae mark the deaths of the most massive stars. So let's get up to speed. So the stars that are going to make supernovae are more massive than the sun. They're maybe 8 times, maybe even 10 times more massive than the sun or higher. And like all stars, massive stars are born in interstellar gas clouds. They need to be very cold because we don't want them to be pressure supported against gravity. So these clouds of molecular gas, you can see these gorgeous images here. And the Orion Nebula is a beautiful example of this. And these stars condense and then begin their lives. And the life of a star is a struggle against its own gravity. So a star like the sun, its gravity is enough to hold in the planets, but the gravity acts on the sun itself, and it would collapse under its own weight. In fact, it would become a black hole if there was no outward force to oppose the inward pull of gravity that's relentless. It's like the Terminator. It absolutely will not stop. And the way the sun supports itself and remains stable is because it's pressurized. The sun is nice and hot. It's got this beautiful pressure gradient that holds itself up against gravity, and it's stable. And the way the sun maintains this thermal pressure is through nuclear fusion in the core. And so there are these nuclear fusion reactions in the sun. In this case of the sun, it's burning hydrogen to helium. In more massive stars, after burning hydrogen to helium, there are phases where then the helium ash becomes fuel and it burns to oxygen and carbon. You can see this little cartoon here, and so forth, making heavier and heavier elements until we get to iron. And then finally, though, once the star has an iron core, that's the most tightly bound element. It's the last thing you can burn exothermically. And so that's the end of the road, basically. That becomes inert. And so once the fuel is exhausted, ultimately the gravity wins the war. The star collapses under its own weight until it becomes ultra dense at the center. And then finally that stops the implosion, which turns around then and becomes an explosion. Most of the star is ejected at high speeds, and that makes a supernova explosion, as you can see in this gorgeous image here. All right. Once supernovae are very important in the life cycles of galaxies and engineer the materials within galaxies. So this is what happens after such an explosion. So this is the remains of an explosion that was thousands of years ago, and it leaves this hot bubble we call a supernova remnant. And to give you a sense of scale, the sort of diameter here is about 100 parsecs. Which is about 300 light years. The distance light moves in 300 years. Or another way to think of it is that's about 1 parsec or 3 light years. That's about the distance between the typical distance between neighboring stars in our galaxy. So 100 parsecs is a big region. So an enormous number of stars are enclosed in this region, all of which was all of this gas was pushed around by one exploding star. That gives you a sense of the explosive power. So another thing that's important for our discussion today is that supernovae are element factories. So I was telling you they undergo nuclear fusion. They actually are the sources of alchemy. They change elements from hydrogen into ever heavier elements until we finally have an iron core and the star explodes. And when it explodes, most of the star's guts, 90% of the mass of the star, is thrown back out into space. And then we can go observe. So here's an explosion that happened 300 years ago. We look at it now. It's still crackling with X-rays. And so that immediately tells you it's very hot. In fact, it's still millions of degrees, even though the explosion was 300 years ago. But we can do even more because we can look at emission lines, atomic lines in the X-rays, and see what the supernova was made of. And here's what we find. We find lots of iron. We find silicon and magnesium, and even more than I'm showing. I'm just giving you examples. And then in blue here, there's a form of titanium. In fact, these are nuclear lines from a radioactive species of titanium, and the lines are made while it decays. And this particular kind of radioactive titanium is known as titanium-44, and it has a high half-life of 60 years. Well, the supernova is 300 years old, so we've already had many half-lives. There's been a great deal of decay, and yet the titanium is still around. And so the supernova made quite a bit. Maybe an Earth's mass worth. But what this also tells you is there's no way the titanium was there when the star was born. It's very short-lived compared to the million-year lifetime of the star. And so what this tells you is, for sure, this is direct proof this star really is, the supernova explosion really is an element factory. And in fact, the titanium was made during the explosion. All right. So supernovae really are element factories, and including making radioactive elements. Okay, so as I said, we're interested in what happens, not just if supernovae go off generally, but what happens if they're nearby. And if they're nearby, if they're close enough, it's not funny anymore. They can actually be a threat to the biosphere. And so this leads to an attack. And the idea is if a supernova is too close, it could actually be a genuine threat to life on Earth. And throughout the literature, starting in the really the 50s and moving on, every once in a while people would write papers about the danger posed by a supernova. And it turns out the main effect is due to the ionizing radiation. So the supernova initially, in the first months and years of the explosion, emits gamma rays, X-rays, extreme ultraviolet, and they destroy stratospheric ozone. So not just make a little ozone hole like you see in the picture here, but wipe it out. And that's bad news because ozone, a stratospheric ozone, shields us from ultraviolet rays from the sun. So once it's gone, there's no shielding. There's incredibly intense ultraviolet from the sun. You and I would put on a hat and sunblock, but if you're a phytoplankton, you don't have that option. And the idea is this kills stuff at the bottom of the food chain and the damage propagates up. It turns out it's even worse than this because then the supernova blast arrives, not the light, but later the blast arrives. And this blast is a particle accelerator. It makes cosmic rays. Those again strip they're also ionizing radiation. They again strip the atmosphere. They also make nasty muon particles, which penetrate deep into the Earth. Those are also bad news. And so when you put all this together, the minimum safe distance is something like 8 parsecs, about 30 light years, which is a very small distance astrophysically speaking. So there's no threat right now. I'm not trying to make 2021 any worse than it already is. But over the history of the Earth, this is very likely to have happened. Okay, so how would we know if we had a supernova near the Earth? Well, if a supernova is close enough, it literally rains its ejecta on the Earth. So let me walk you through this story here. So first, let's zoom back to sort of interstellar scales. And this is a little simple-minded simulation of a supernova explosion in a nice uniform density interstellar environment. And you're seeing the blast sweeps up the gas into this dense shell. And then there's this hot, low density region left behind. And I'm running the movie along. Which I've drawn a circle here at 10 parsecs, which is about this kill distance. And what you're supposed to notice is if you sat there, and you probably don't know how well you can read the clock, for many thousands of years, up to even 100,000 years, the blast wave goes by. So now let's ask what would happen if this blast wave encounters the solar system, and now zoom way into solar system scales. And so now, what you're seeing here, the little circle here is now supposed to be the sun at the sort of center of the picture, and then there's a circle at 1 astronomical unit, which is the orbit of the Earth. And then I'm whacking it with the supernova blast, and you're seeing the first, I don't know, couple weeks of many thousands of years of trouble. And what you see is this supernova blast pushes back the solar wind, and the Earth can find itself inside supernova debris. That's actually quite a nearby supernova. That's quite a dangerous supernova, actually. So supernova debris literally rains upon the Earth, particularly in the form of the heavy elements which condense into these small particles we call dust, stardust. So the question is, how would we know? So after the fact, maybe millions of years after the fact, how will we know that this has happened? And so supernova material has rained upon the Earth, so we need to find a way to dig up geologically material where we can point to it and say, yes, that's a fingerprint of a supernova. I know that's extraterrestrial. And so that's the idea. And now for the bad news. The amount of supernova debris that actually lands on the Earth it would be a lot if it all fell on your head at once, but for every square centimeter of the Earth, it's not very much at all. In fact, it's a little less than a microgram of supernova material for every square centimeter. That is not very much. That's not going to leap out at you. There's not going to be some visible layer. That's the bad news. So it's a tiny signal, which means we're going to have to be clever. We're going to have to use isotopes in some ways. Now, we could use the stable elements the supernova makes, which remember are things you've heard of: iron, silicon, oxygen, magnesium. Those are great, but the problem is we are also made of them, which is not a coincidence. We are ultimately the children of supernovae. But because we're already made of these things, just finding them doesn't prove they came from a supernova. But this is why I was so obsessed about radioactivity. If we can find radioactivity that's still live, that is, it's unstable, but these nuclei have not decayed yet, then the idea is there's none left on Earth. We have lifetimes of millions of years. There's none left on Earth. Even if the Earth was born with this stuff, it's long since decayed. But if it's live now, that means it has to have come from the supernova. So that's our trick. That's our remote sensing trick. And the analogy here is green bananas. Like radioactivity, green bananas that are unstable, they want to decay. And if you find green bananas in Illinois or in the Commonwealth of Massachusetts, you know two things. One, they were made recently, and two, they were not made locally, so something had to bring them. So our live radioactivity is just like green bananas. If we can find live radioactivity, undecayed, those are green bananas. They had to be made recently, and then they had to be brought here by a supernova. So that's the idea. And we'll be particularly interested in one kind of radioactivity, which is an isotope of iron, which is iron 60. It has a half-life of about 2.6, 2.7 million years. So that's great. But I already told you there's a tiny supernova signal, and the radioactive part of the signal is even less. So that the signal we're looking for is tiny, tiny, tiny. The amazing thing, though, is that it's actually been found. So there's actually geological evidence for this, and the problem really got interesting about 2004. And so it involves this rock, which is called a ferromanganese crust, and it won't take me long to tell you what I know. So in the picture, there's a coin that's about this big. It's about the size of a $50. And so that means it's a rock you can fit in your hand. And these things live on the bottom of the ocean. What happens is there's rocks on the bottom of the ocean that grab iron and manganese and other trace elements from the water, and they attach to the rock. They bond onto it. And this crust, called a ferromanganese crust, because iron and manganese, it grows very slowly, just millimeters per million years. It's an incredibly slow growth. And so this rock that you can hold in your hand is then sampling many millions of years. So it holds on to history. And so then you dig into the rock, it's like tree rings. The deeper you go, the further in the past you're going. And so this rock was analyzed. Here's 2, 4, 6, 8, 10 million years ago. And these guys looked for this iron 60, this radioactive iron. And you can see two features in this plot. So this noisy part is noise. That's the background to their measurement. For the experts, that's the stable isobar. So that's just the limit of their ability to measure at the time. That's nothing. If that's all they found, it would be boring. But of course, the interesting thing is this. They found this nice, beautiful pulse. So that's good news. Those are our green bananas. That's an actual signal of iron 60. And so they find this pulse. Just like they're supposed to. You can even date when it is. It's between 2 and 3 million years. That's fantastic. Now, to give you an idea of the amazingness of this measurement, the signal is incredibly tiny. The ratio of iron 60 to ordinary iron is 10 to the minus 15. So this is just an amazing thing. And so to do this, you need a big contraption. You need this accelerator here to make this measurement. So this is called accelerator mass spectrometry. Ordinary mass spectrometry is not good enough. You need an accelerator to do this. And you can see one of the graduate students who did the work here for scale. All right, great. Oh, and that was in 2004. I just want to make clear that there's been a bunch of new work. So since then, and just in the past few years, it's gotten really exciting. There have been more measurements in these crazy undersea crusts, also ocean sediments, which are interesting because they give us more information about how long the signal lasted over time. There's a whole story I can tell you about magnetic microfossils. Ask me about that. If the stuff was delivered to the Earth, it should have also been delivered to the moon. And in fact, it was. So lunar samples, Apollo samples have been examined, and indeed, they contain iron 60 as well. Cosmic rays themselves, high energy particles, also contain iron 60. So again, green bananas, they had to be produced recently and brought here. And then finally, there's a candidate for the cinder, the leftover center of the exploding star, which is now known as a neutron star. There's a candidate that looks like it might be the thing, it might be left over from the explosion. So there's a lot going on. So just to summarize, before, this is the data I just showed you replotted, and now there's all this new data. There's too much going on here. I don't have time to unpack it. I'm just trying to give the impression there's a lot of data now. And now everybody agrees there's a pulse 2 to 3 million years ago. There might even be a second signal earlier. So we have samples from all over the Earth and on the moon. So we really know this happened 3 million years ago. Near-Earth supernova explosions happen. All right. But as if that wasn't enough, now let me take you to Antarctica. And now I have to confess, this is not work I've done myself, but I'm a huge fan of it. So I'm reporting very hard work other people have done. So this work was not done at the South Pole. This was done at a German research station called Konen Station. You can see it here. And you notice that it's both inland, but it's not all the way to the pole. And it turns out it's at quite a high altitude. And that's a good thing because it has sort of minimal terrestrial dust, which is a good thing for them. You can also see the picture here that it is incredibly remote and small and kind of lonely. So it's kind of freaky. I would be a little freaked out to go there, to tell you the truth. And so to do their remote sensing, there's several steps to this. First, they took 500 kilograms of snow, very recent snow, so just basically from the top layer. This is not them actually taking these samples, but I think it's a similar idea. And as you can see, this is a small station. This is not high tech. So this involves people with shovels. And a lot of shovels because it's 500 kilograms worth, it's half a ton. Then they pack it up and it got shipped, I think initially by plane, but ultimately by a boat went through South Africa, then all the way to Munich, Germany, all the way keeping the stuff cold. And then in Germany, now the technology gets a little higher. The snow is melted, which is not a trivial exercise, by the way, for a half ton, and then filtered with a 3 micron level filter. And then the samples were put through this accelerator that I mentioned before, which you need to do this ultra high precision mass spectrometry. And of course, I wouldn't be talking to you about this if they didn't succeed. So there's this beautiful physical review letter paper on interstellar iron 60 in Antarctica. And so, and this is Dominic Cole, who is the graduate student who, of course, did all the work in the laboratory. And indeed, they searched for iron 60 in this recent Antarctic snow. So they melted the snow, collected the residue, as I mentioned, analyzed it via this accelerator mass spectrometry, and indeed, they found iron 60. Now, to be a little more honest, what they really found is not enough to find iron 60 because there should be a small amount that falls on our heads because interplanetary dust particles, small particles, meteorites get bombarded by high energy cosmic rays, and that makes some small amount of iron 60. So you have to show it's in excess of that. And they showed that. I can tell you more about that if you're interested. Oh, and you also have to show that it's not due to anthropogenic sources, which are a nice way of saying nuclear bombs and nuclear accidents. And they also could demonstrate that it wasn't that. Again, I can tell you more about that if you like. And so it doesn't come from the Earth, it doesn't come from interplanetary space, it is not only extraterrestrial, but extrasolar. And so they found iron 60 in the Antarctic snow. Now, I told you there was a supernova that put stuff 3 million years ago, but now we're seeing it in Antarctic snow that's younger than you are. So how did this stuff get here? And there are two basic ideas. One is this blizzard of material from the supernova, which made this big pulse 2 to 3 million years ago. The storm isn't quite over, it's still a drizzle today. And there's another idea that maybe what happened is it turns out the sun is embedded very locally in a little cloud, and maybe some of this stuff got embedded in the cloud, and now we're running through it, and it's falling on the Earth. And actually, those two stories don't even have to be in contradiction to each other. They can actually work together. So another thing, just to mention Antarctica that we're excited about, it's just recently been discovered that Antarctic ice goes back quite a long way. Until recently, it was thought Antarctic ice doesn't even go back 1 million years, so I can't use it to go see my supernova. But recently, it's been discovered that some Antarctic ice goes all the way back to 2.7 million years during the interval when this supernova signal has been received. So there's some hope of looking for the supernova signal in Antarctic ice, as well as other deep ocean samples. All right. So I know we're running out of time. So there's really only one conclusion I want you to take away from all of this. And my one conclusion is this is a thing. By which I mean, this started out as this crazy hobby, but now this really is bona fide astrophysics. This is a new kind of remote sensing. It's another way of bringing extraterrestrial material in the lab, like meteorites, like these things called pre-solar grains. And okay, maybe there are a few other things I hope you could take away as well. So live iron 60 has been seen globally and on the moon. We see this beautiful signal 2 to 3 million years ago. It's now seen in Antarctic snow, so it probably means the storm is still now a drizzle. What's so beautiful about this is it's so interdisciplinary. There's all kinds of astrophysics that this involves, but even going beyond astrophysics, it involves heliophysics, nuclear physics, geology, even biological evolution. I wouldn't want to leave you with the impression there's no work to do. On the astrophysics side, we'd like to know a lot more about the supernovae that made this iron 60, what mass they were, where they were. And so if we can get more measurements of the moon, there's some interesting things we can do with that. We'd like to get more data from cosmic rays. I mentioned we think we found a potential neutron star that could be the leftover remains of this supernova. And I could tell you more about supernova dust. We'd like to see more in different samples, other isotopes. I could tell you a bit about those. I mentioned now Antarctic ice is in play for directly seeing samples from this supernova. It turns out the supernova 3 million years ago was sort of a near miss. It wasn't quite close enough to cause a big mass extinction, but there may have been some biological damage, and people are actively looking at this. And then finally, once we've gotten our minds around the idea that there can be near-Earth supernova explosions, it's interesting to ask that maybe in the further past, in the deep past, could there have been even a supernova associated with the mass extinction? And we've got some ideas about that as well. So there's lots more yet to come, so please stay tuned. But for now, thank you for your attention.
Thank you so much. This is, I think, a very interesting topic, and I was very intrigued. And we have a good and diverse audience coming both from the Media Lab, but also from Harvard CFA, different departments at MIT who are introducing themselves. If you've joined since the initial introduction, feel free to leave an intro in the chat if you're from outside our department, and I'll go ahead and open it up to questions. So you can feel free to use the little hand raise feature in the chat, and I can look out for anybody who uses that. But you're also welcome to just jump in with any questions to Brian about this area of research. So anyone want to kick us off?
I'll kick us off. Can you hear me?
Yes.
Yeah, please.
In the 90s, I read a paper in PhysRev that also indicated that nearby supernovas could have such energetic neutrinos that they would actually interact biologically and be bad news.
Very good.
And I vaguely recall that might have actually not been a good, that may not be supported, but have you heard of that and have you looked at this?
Yes, thank you. That's great. Yeah, on the longer version of the talk, I exactly talk about that. So if you're not familiar with supernova explosions, in fact, what I didn't have time to talk about, but is super beautiful, is that actually supernovae are neutrino bombs. So most of the energy of the explosion, most of the energy, the gravitational energy liberated in creating this neutron star, most of that energy comes out in the form of neutrinos. The little optical fireworks we see are very nice, but they're less than 1% of the total energy. So really, they are neutrino bombs. Most of the energy comes out in neutrinos, these ghostly invisible particles. And so yeah, Juan Collar, who's now at University of Chicago, wrote this really clever paper where he worked out the number of neutrino interactions per unit of gram of meat. You only get about 1 interaction per gram, even for a really close supernova. But he argued that these interactions would be sort of tuned to be particularly bad for DNA, and so basically everybody gets cancer. And that'd be really bad, because if you knew a supernova was coming, if you had to make a shield for the photons, I mean, if you had to, you could do it. It's a big project, but it's life or death. But neutrinos, you can't run and you can't hide. But fortunately, a health physicist, you remember right, a health physicist ended up looking at this and said, no, it's not as bad as all that. So the supernovae are dangerous, but actually not because of the neutrinos. Or if they're close enough where the neutrinos are dangerous, you have worse problems. That's not the first thing you'd worry about. Yeah. Very good.
Good question to kick us off. Anyone eager to follow? Otherwise, I can also jump in.
I'm curious about the moon measurement that you mentioned.
Yeah.
And I wonder, would that allow us to know whether the live isotope that you found are from the same supernova or from multiple supernova?
Oh, that's a great question. Yeah. So in some ways, let me see if I can talk and digest the slides at the same time. In some ways, the moon has some disadvantages because, right. So in some ways, the moon has a, right. So we can use the moon as a telescope, because one of the nice things is when that the moon doesn't have an atmosphere. So when the stuff lands on the Earth, the atmosphere, it takes a while. It takes years for the stuff to make it from the top of the atmosphere to the ground, and they get all scrambled up. So you lose information about direction. Right, that's what this says. But the moon is airless, and so we did a simulation. Now, this is an example of 2 different directions the supernova could be, and if the blast comes as sort of a plane wave, then by looking at the pattern, the color bar here is the abundance of iron 60, where red is a lot, blue and black are not much. And so depending on where, these are 2 possible locations of star clusters, and depending on where the supernova was, you should see a different pattern on the moon. And you can see the Apollo landings are here. And there actually are some data, but they're down below, but they're too ratty to tell you anything now. But now that we're going back to the moon, it would be super interesting to look at the abundance as a function of latitude on the moon. That's a super good question. The downside of the moon, though, is the stuff just sits basically at the top of the moon, so it doesn't accumulate like ice, and so we can't date it very well. So the downside is we can't date it, but the upside is we may learn something about the directionality of the supernova. Great question. Thank you.
Yeah, I think treating the moon as a directional sensor
is an antenna. Yeah.
Is an antenna. It's very interesting. So let's take one more question from Michael Foley, and then we'll hopefully, Brian, are you able to stick around a little?
Yeah. If you have more questions, I love talking about this, so I'm happy to stay. I don't want to muscle in on Justin's time, though.
Okay, great. So we'll hear from Michael, one more. We'll switch over, and then we can have an open discussion after the talk as well.
That's good. Thanks, Juliana. Awesome talk, Brian. Thank you very much. So I had a quick question. Do you think that there's a way to potentially, go back even farther in time? I'm thinking particularly trying to constrain the timing of supernovae that may have produced a local bubble over the last 20 or so mega years. So.
Yeah. Beautiful. Yeah. Very good. So right. So another thing which I didn't have a chance to explain is the solar system lives in a low density, high temperature bubble, which we call the local bubble. And indeed, just as Michael says, the people who study this, completely independent of this crazy iron 60 stuff, already worked out that you need something like 10 supernovae over the past 10, 20 million years. And so this 3 million year thing would be one of the more recent explosions that helped to carve out this local bubble. And so we're very interested in, so iron 60 will start to decay, like the lifetime, we start to run out of iron 60 if we wait too long. But there are other isotopes that are of interest. and there are samples that go further back, but these crusts can go back tens of millions of years. So that is not out of the question. We're writing something right now actually about exactly this. So yeah, that is absolutely an interesting and thing to do, which I think is doable. Yeah. Great. Thanks for your question.
Thanks.
All right. Thank you very much again, Brian. And let's turn it over to Justin Vandenbroucke.
Okay, can you hear me okay?
Yes.
All right, let me just set up my sharing. And can you see that okay?
Yes, we are seeing your screen.
Great. Thanks to Joe and Juliana for the introduction, and to Brian for his great talk on this idea of using Antarctica to detect interesting astrophysical events. And especially that question a couple minutes ago about neutrinos from these nearby supernovae. That's a great segue to this topic. Some of you might know that supernovae, and as Brian mentioned, supernovae produce a large fraction of their energy in neutrinos. Those neutrinos are low energy compared to the ones that we're interested in with this experiment. So those, if you're familiar with the electron volt, that's the energy unit that we use in particle physics. It's the energy that an electron gains in kinetic energy across a 1 volt, traversing a 1 volt potential. The energy of the supernova neutrinos that have been detected so far are at the million electron volt, mega electron volt scale. What I'm interested in is the even higher energy scale at the tera electron volt, trillions of electron volts, even up to peta electron volt, 10 to the 15 electron volts. And so we're zooming out in energy, and we're also zooming out in distance. So from the kind of the local galaxy near the solar system, all the way out to beyond the galaxy into extragalactic and cosmological distance scales. So the project I work on is called the Ice Cube Neutrino Observatory. Here's a photo. The photo is not literal for the underground colored blobs. That's an artist's collage. The actual color dots there represent an actual neutrino that has interacted in the ice, collided with the ice to produce a flash of light that's been recorded at these dots by our sensors that are deep under the ice. So that's actual data from an actual neutrino interaction in the color dots. It's just that that's been superimposed on this view of our detector building. So I think this topic that I'm passionate about in general is known as multi-messenger astrophysics, and it's really a great match for this series on adventures in sensing. Another name for multiple messengers in astrophysics might be called multi-sensorial astrophysics. If you think about the history of astronomy and astrophysics, for thousands of years, as long as humans have looked up at the night sky, they've been trying to understand the stars, trying to understand the night sky, and they started that with their own eyes, and then with telescopes that could magnify and amplify the signal, and still using their own eyes, and then gradually branching out into more sophisticated sensors across the entire electromagnetic spectrum over many orders of magnitude in the electromagnetic spectrum. The new revolution just in the last few years is to be able to use not only the entire electromagnetic spectrum, but also to use other sensors. In other words, other senses. So using light, of course, is the sense of sight. Neutrinos are subatomic fundamental particles. They're kind of like electrons or muons, but they don't have electric charge. So they only interact very weakly through the weak interaction. And they come in 3 different flavors: electron, muon, and tau. And so you might extend this analogy and say that they have 3 different tastes. And so this is the sense of taste that we're using with neutrinos. You've probably also heard about gravitational waves. That's been a major revolution in physics the last few years. And that's these ripples, these vibrations in the fabric of space-time itself. And you might think of that as analogous to sound waves. They're actually more exciting and more fundamental than sound waves because it's not a gas or some other medium that's waving, it's actually space-time itself. But you might, again, as an analogy, think of that as the sense of hearing. And so we have these 3 senses that we're now studying the universe with. There's also a 4th one that's been around for a while, which is cosmic rays. And so these are not photons, they're not neutrinos, they're not gravitational waves, but they're charged particles, including protons, electrons, and so on. And I'm not sure, there's not an easy way to map those onto the senses, but you might call that touch or smell. And so here's an illustration of an astrophysical It might be a large hadron collider. It's some type of naturally occurring particle accelerator, which is working at energies even higher than the highest energies humans have ever reached in their human-made accelerators on Earth. And it's producing energetic particles, which could include cosmic rays. And it's also, in this case, producing neutrinos and photons, including the highest energy photons, gamma rays. And so we're interested in viewing the universe in these 4 different complementary senses to get very different views of the universe. It's kind of like looking at a person with visible light or with X-rays. You get a very different view of what's going on, and you get complementary information. So what produces neutrinos? They are due to nuclear interactions, and we have detected them over a huge range in energy scales, similar to the electromagnetic spectrum. Here's an array of different sources from which we have detected neutrinos. They're superimposed on this curve, which gives the cross-section. The cross-section is basically the effective interaction area that a neutrino presents to another particle when it collides, which quantifies the probability of interacting or colliding with that particle. It's measured in millionths of a barn, and a barn in turn is 10 to the minus 24 square centimeters. So these are very low interaction probabilities. So at the lowest energies, we think that neutrinos exist left over from the Big Bang. We know that there are radioactive elements throughout the Earth naturally occurring that also produce neutrinos through their radioactive decays. We know that reactor operations also produce fission fragments, which are neutrino sources. We know that the sun produces neutrinos as a byproduct of the fusion that powers it. As we've discussed, supernova are very bright sources of neutrinos. And in fact, we have detected neutrinos from one nearby supernova in the Large Magellanic Cloud a few decades ago. When cosmic rays themselves, these are the energetic charge particles, when they collide with the atmosphere, they undergo nuclear interactions, which produce neutrinos. And then marching up in the energy scale, human-produced particle accelerators can also produce neutrinos. Basically, anywhere you have energetic nuclear or particle physics interactions, there are likely to be neutrinos involved. Now we get to the region that I'm most excited about, most interested in, which is galactic and extragalactic. So the only source of neutrinos that we've detected from outside the solar system so far is the supernova in 1987, until this new field that I'm discussing now, which is looking at larger distance scales and larger energy scales, all the way up at 10 to the 12 electron volts and above. And that's looking for sources of neutrinos within the galaxy and even beyond the galaxy, and from other distant galaxies or other sources beyond the galaxy. So how does our sense of taste work with this neutrino detector? First, to describe a little bit about the interaction mechanism, I'll start with an analogy. You've probably all seen boats or birds swimming on lakes and seen that they produce a wake. And the basic mechanism for that is that this source is producing a disturbance in the material, in a medium, and that the source is traveling across the lake faster than that disturbance is propagating. And therefore, the wavefronts are kind of piling up on top of one another, and you get this cone effect. It's the same idea as a sonic boom as well. So that's a wake produced by a duck. If you have a charged particle traveling through a medium, it's also producing a disturbance. And if that particle is traveling faster than light can travel through that medium, that is, if in the medium, the speed of light is slower than the speed of light in vacuum, but the particle is faster than that speed of light in the material, then it can also produce this analogy to a wake or a sonic boom. And that's known as Cherenkov radiation. So here's a large number of subatomic particles produced at a nuclear reactor, which is producing this diffuse glow of Cherenkov radiation, which is typically peaked in the blue into the ultraviolet part of the spectrum. So that's the fundamental mechanism of this sensing technique that we use for detecting neutrinos using Cherenkov radiation. Now, these have to be charged particles that can produce this signal. So the basic idea is that when a neutrino collides with an atom, including an atom of ice in Antarctica, it makes other subatomic particles, including charged particles, which in turn then make a flash of this Cherenkov radiation. So all we have to do then is find a very large, remember those cross sections are very small, So we need a very large detector where we can monitor a large number of atoms for these Cherenkov flashes. And then in order to instrument that large volume cost effectively, we need it to be transparent over a large distance so that we can instrument it relatively sparsely with sensors. So if you think about naturally occurring media around the Earth that are clear, that are transparent in this blue and ultraviolet regime, you might think of large bodies of water or salt or ice, and all of those have been considered. Some of them have been instrumented. And one of the best places on Earth, one of the clearest large bodies of naturally occurring medium is ice in Antarctica. So that's what we did. We drilled 86 holes. We installed light sensors into them, over 5,000 individual light sensors. Each one is a photomultiplier tube sensitive to single photons, about 10 inches in diameter. And inside of this spherical housing, in addition to the single photomultiplier tube, we have electronics to provide high voltage and readout electronics. So we get a digital signal from this module. That digital signal is then propagated upward on the cable. The cable provides both mechanical support and high voltage, as well as propagation of the digital signal. That then goes up to this above ice building, which was shown on the first slide, which we call the Ice Cube Lab, which is basically a 2-floor building, which houses a lot of computing to manage all of the data and control the detector. So these 5,000 sensors, they're spanning a cubic kilometer of ice. That's why we call it Ice Cube. The mass of that is 1 billion tons. So we're monitoring 1 billion tons of atoms for interactions of individual neutrinos. These sensors have precision ability to detect individual photons. They also have precision timing. So with about 1 nanosecond resolution, we can identify the number of photons and the time that they arrived at each of these sensors. And by combining the timing and the location, that's how we determine where and when each neutrino arrived. And from that information, we can estimate its energy and the direction from which it arrived. That's how we're not just detecting neutrinos, but doing neutrino astronomy with them, because we can calculate the direction of the neutrinos and therefore do astronomy with them. So the main driver for this is neutrino astronomy, neutrino astrophysics, and that's where my passion is. But there's really a wide variety of interdisciplinary science that we can do. So all these different topics on the perimeter here, divided into these few different categories. So we can do a wide range of astrophysics studies, but we can also do particle physics. We can constrain the properties of neutrinos. We can measure their mass and their oscillation parameters. We can search for dark matter, try to identify the nature of dark matter, other fundamental particle physics topics, and searching for exotic particles like monopoles. We can also do interesting earth science, glaciology and geophysics, because we have this precisely instrumented large volume of glacial ice in the ice sheet, which has been laid down over hundreds of thousands of years. Okay, what do our signals look like? So I showed before an illustration of a cosmic ray traveling across the universe, and associated with that might be neutrinos and gamma rays. And the same process can occur when that cosmic ray collides with the Earth's atmosphere. So here's an illustration of kind of a chain reaction of particle physics interactions when that cosmic ray proton collides with an atom of air. In this case, it makes some pions. Those pions then decay into gamma rays and electrons and positrons and muons and neutrinos. This component of this is called an air shower. This component of the air shower is typically absorbed within the atmosphere, and this component, the highly penetrating particles, the muons and neutrinos, can reach all the way down to ground level. So if we detect neutrinos or muons, they might have come from this process, from cosmic rays colliding with the atmosphere. Or if we detect a neutrino, it might have come from beyond the atmosphere, from an extraterrestrial source. And so there's a lot of science we can do with these air showers themselves, but if we're interested in identifying extraterrestrial neutrinos, we need to think of this as a background and search for the signal on top of that. I mentioned that the Cherenkov flash is only produced when a neutrino produces a charged particle. One of the most efficient ways for that to happen is to produce a muon. So a neutrino can produce a muon, but a cosmic ray hitting the atmosphere can also produce a muon. So that's kind of an overview of the signals and backgrounds that we're dealing with. So these muons produced by air showers sum up to about 70 billion per year. That's several thousand times per second we're detecting these muons. And there's actually a lot of science we can and have done with those themselves. Within that haystack, there's this needle, which is the atmospheric neutrinos. So that's this neutrino here, that's 1 in 1,000 of those. And then among all of the neutrinos, parallel to this process is the ones that have traveled all the way across the universe before colliding with the ice. And those are about 1 in 100,000. So we're kind of looking for a needle in a haystack inside many fields full of haystacks. So there's a lot of interesting signal processing and statistical methods to identify these signals. Now, these highly penetrating particles, the muons and the neutrinos, they reach ground level after traveling through the atmosphere. They can even reach deep underground, but a muon cannot travel very, very deep underground. They can't travel all the way through the Earth, but the neutrinos can. So one clever idea we have is to look from the South Pole up through the Earth at the Northern Hemisphere. And if we see a signal there, then it's produced by neutrinos traveling through the Earth because muons cannot travel through the Earth. And that was actually the basis of this cartoon kind of logo of our predecessor called Amanda. So Amanda was kind of the forerunner prototype for IceCube. And the logo was this penguin looking through the Earth for a neutrino traveling all the way through the Earth, using the Earth to filter out the background muons. A little bit more quantitative view of that. Here's those components of signals and backgrounds again. Muons produced in the atmosphere, neutrinos produced in the atmosphere, and neutrinos produced in astrophysical sources far away. And here are the numbers for the rates of those. Depending on the energy threshold you apply, we get about 10 astrophysical neutrinos per year above this energy. So how do we do this needle inside a haystack, inside many haystacks? We have two main handles to do that. One is the direction of the neutrinos that we detect, and one is their energy. I said that we can use the Earth to filter out the muons. So that means if we detect a downgoing event, it could be from the atmosphere, but an upgoing event is much more likely to be a neutrino rather than a muon. So here's a quantitative view of that. This is the rate on the vertical axis as a function of the direction on the horizontal axis. And you can see the muons basically cannot reach the detector from the upgoing direction from the northern hemisphere, but they can reach it from the downgoing direction from the southern hemisphere. We can also use the energy. So here's kind of a region of flux versus energy at the highest energies of neutrinos. We have this atmospheric signal of neutrinos from the atmosphere. The nice thing is it's very steeply falling function of energy. And so if we find a higher energy component of neutrinos sticking out above that background, then that's another nice handle to distinguish signal from background. So that's kind of the basic idea of how we built the detector and what its purpose is and what our basic signal and background sources are. I want to spend a couple minutes on how we actually built the detector. I was fortunate to get involved in the project originally as a grad student during the early years of construction of IceCube. So the way I spent 3 summer seasons there helping build IceCube. The way we get there is we travel through several flights to get, basically we hop to, first it was, at the time I was in San Francisco, to LA, to Auckland, New Zealand, to Christchurch, New Zealand, then to McMurdo, and then from McMurdo, another final flight to the South Pole. So McMurdo was a fun place to hang out and see penguins sometimes. Then the final flight, it's typically about a week of travel just to get from home to the South Pole. On the final leg of the trip, then approaching South Pole, it might look like this. You can see multiple different buildings here. Here's that IceCube lab that I mentioned, a couple other research buildings, the large station where people live and work. This is a much larger station than the one that Brian showed. And you land on, instead of runway, we call it a skiway, because the South Pole is sitting on about 10,000 feet of ice. That's our detector, and the bedrock is just barely above sea level. So you're also at about 10,000 feet of altitude landing on this ice. So this is the Amundsen Scott South Pole Station. It's a great place, a great facility for all kinds of different research. It's a site of international peaceful cooperation in the name of science. That's mostly true, although here's a photo of when I was actually being beaten with the South Pole. So people might not realize this, the South Pole is actually a physical thing. There's a marker there. And so you can pull it out of the ground. And this was actually my friend, my colleague in grad school. But no scientists were actually harmed in the taking of this photo. We were just staging the photo. So zooming out again, here's a photo of an aerial photo of kind of a plan view instead of that diagonal view from before. Here you can see again the station, the skiway, and the footprint of the ice cube detector. So it's 86 strings spanning this square kilometer or cubic kilometer. How did we construct it? Here's an illustration. The basic idea is that we just pumped hot water to as high a pressure and as high a temperature as we could and let it melt the ice. And we could do that with a lot of engineering and optimization. We could do that pretty efficiently and pretty powerfully and pretty quickly. It was a huge engineering challenge and then a huge construction challenge. There were some hiccups in the first year or two, but then we really got it down to a smooth operation. So here's an illustration of what that looked like. That's the drill tower with the hose reel you could see. We first went down with kind of a hot knife approach. So those are just copper pipes with hot water circulating to melt through the snow layer that's on the top, and then repeated with a different drill that squirts the actual hot water. And then let it keep hanging like a plumb bob and squirting the hot water, recirculating cold water from the surface, heating it up, and then injecting it at the bottom, and continue that all the way until you reach 2,500 meters of depth. Here's a photo during the construction process. Here's the drill tower, here's the hose reel, and here's a shipping container for scale. So pretty big operation. Here's what it looked like during construction, standing over one of these holes. And I said the depth of the hole is 2.5 kilometers. The width is just barely wider than a person's shoulders. So that's pretty spooky to stand over it. And we had a lot of discussions of hypotheticals of what would happen if you fell down the hole. Of course, there are a lot of safety precautions in place. There was a big lip covering the hole, so you couldn't actually fall down unless you really tried to feed yourself into the hole. Some more photos of construction, another sensor going down into the hole, sensor being prepared to go down in the hole, and people around the hole. There's that lip for protection you can see there. So as soon as we turned on the detector, we detected the highest energy neutrinos, the full detector. We detected the highest energy neutrinos that have ever been detected. So here's a pair of them. We named them after Muppets. Here, Bert and Ernie to start with. If you've been to Madison, here's a sense of scale. Or if you're familiar with any typical college campus, here's the campus and here's Bert superimposed on it for scale. So this is what it looks like to have 10 to the 15 electron volt neutrino deposit all of its energy in ice and then overlaid over the campus for scale. We then lowered our energy threshold and basically were able to detect a large number of additional events. So we detected 26 additional events for 28 total. And then with this higher statistics, we were able to say not only that these are the highest energy neutrinos ever detected, but they cannot be produced within the atmosphere or within the Earth. So they must be coming from the universe. And in fact, this was a very bright signal, as bright as basically the most optimistic theories had predicted. And so we showed that the universe glows brightly in these TeV to PeV energy neutrinos. This was published in 2013. Physics World magazine named it the breakthrough of the year in that year. And since then, we've continued improving our measurement of the energy and spatial distribution of these neutrinos. And the big mystery, of course, is what's producing them. So the first thing we do, of course, to try to answer that question is make a map of where on the sky they're coming from. I mentioned that this is neutrino astrophysics, neutrino astronomy. That means that we can calculate the directions. And so if you make this map of the sky, this is a 2D projection where you're basically projecting the Earth's coordinates out onto the celestial sphere. You can see these X's and crosses mark the directions of the neutrinos, and you can see they're roughly roughly compatible with isotropic. So they're not forming a line on the sky. This gray line, for example, is the galactic plane. They're obviously not correlated with the galactic plane. And therefore they're consistent with isotropic. Therefore, they're likely extragalactic. And so we're looking for extragalactic source populations that could be producing these. You can brainstorm what your most favorite source would be that could be producing these. We can discuss more in the discussion, but I'll just go through a couple of possibilities. One is, of course, other galaxies, maybe those similar to the Milky Way, maybe those that have a much higher rate of star formation and supernovae. Maybe supernovae themselves, we know they can produce MEV neutrinos, but there are also ideas that they could produce these much more energetic neutrinos. Maybe they have something to do with black holes, either the black holes that are comparable to the mass of the sun, or those that are much larger, millions or billions of times the mass of the sun, which are at the center of distant galaxies. And in fact, we've detected so far one source, and it is one of these. So it's a supermassive black hole at the center of a distant galaxy. A little bit on how that works, how that analysis works. We basically did this analysis that I showed you before to detect this diffuse signal. We did that over several years using sophisticated blind analysis techniques. Once we had developed all of that, we could run it much more quickly. So now we can identify one of these high energy neutrinos within less than a minute from the time it collides with the ice until the time we can automatically publish publicly on the web that such an event occurred. And so we provide to professional as well as amateur astronomers this real-time alert stream. And the 10th such alert was followed up by dozens of observatories around the world, including gamma ray observatories, and they found this signal. The dots and the contours here represent our direction calculation for the neutrino. The background color map in violet is a map of the same patch of sky in gamma rays. And so this individual neutrino is very likely from the same source as those gamma rays, which is one of these very massive black holes kind of across the universe. So that's really exciting. That's the first source that we've identified. We know if you simply do a similar search for neutrino sources in every patch of sky across the whole 4 pi sky, and compare that to the size of the diffuse, let me back up a minute. You do the search over the entire sky. You don't find sources in any location except for this one that we've seen so far. And then you compare our sensitivity to our total magnitude of the flux that we've detected. If you compare those two, you know that there must be at least hundreds of individual sources that's making this diffuse glow. And so we know that we've detected one source and there must be at least hundreds of them out there. So we're really just beginning this new field of neutrino astronomy. So here's kind of a timeline illustrating that. The idea was conceived, the basic idea of neutrino astronomy was conceived originally in the 50s. This modern idea, this incarnation of doing it in AiS was in the 80s. Then we had this predecessor detector. We detected the IceCube detector about a decade ago, discovered this diffuse bright glow of neutrinos within a couple years of finishing building the detector, then identified our first source a couple years ago. Now we're starting to see emerging evidence of additional sources as well, but we're still building up statistics on that. Before I conclude, I just want to give a quick advertisement for another sensing project that you might be interested in. This is closely related to neutrino astrophysics and multi-messenger astrophysics, but it's detecting cosmic rays rather than neutrinos. And the idea is that instead of using a professional particle or astroparticle detector, you can use your own cell phone, your own smartphone. And so when one of these energetic particles, either from cosmic rays or from background radioactivity, interacts inside a smartphone image sensor, it deposits a track. And that track is very analogous to what a professional detector might record. And so you can download the app, run it, analyze the public data set of images and so on. It's called the Distributed Electronic Cosmic Ray Observatory. So to conclude, here are the three senses that are especially exciting in modern multi-messenger astrophysics. South Pole ice is one of the clearest solid substances or dense media on Earth, great for neutrino astronomy. We detect a huge number of these particles. We're doing a wide variety of science with them, including detecting about 10 of these very high energy astrophysical neutrinos per year. And we know we've measured that the universe is glowing very brightly in these neutrinos. So it's like the first new type of image of the universe using this new sense. We don't yet know what's producing those neutrinos. There are a lot of interesting mysteries there. We've only identified one source so far, and we know there must be at least hundreds of them out there. And that's it. Thanks a lot.
Thank you so much. That was a beautiful talk. I love how you moved from some of the science to images of your own adventure to Antarctica, and then speculating on some of the origins of these neutrinos. So does anybody have questions for Justin about the IceCube experiment? You know, some of you guys joined us today with specific interest in IceCube. Anyone?
Maybe I can kick off with a quick question. Certainly it'd be great to ask some physics questions, but first a technical question. How well is it held up? I mean, you've got lots of phototubes and these smart detectors. They've been out there for a long time. How often do you have to replace one, or do we even do that, or you just put a new string in? And I'm also interested, what kind of network do you use? Is it Ethernet? Because you could do that and just have them work with IP coming up, or do you have your own protocol for the network going down?
Yeah, good questions. So when we drill these holes with hot water, there's a standing column of hot water. And then we don't pump it back up. And so, except to recirculate it as hot water. And so you can't see the water level in this photo. Actually, you can see a little bit of a reflection there in the center. That is the water level about 50 meters down. And so the water column refreezes around the sensors after we install them. That means it's equivalent to like launching a satellite. There's no maintenance we can do after it's frozen in. We can communicate with it. We can install new firmware. We can take data and so on, but we cannot mechanically service it. They're performing very well. A decade later, basically almost all of the failures we had were right after installation. So the refreezing process, as you can imagine, is pretty stressful. A small fraction of them, I think maybe 1% died during that process, but they basically have not died since then. So it's performing well. The protocol we use, it's a custom protocol. It was designed by an engineer in Germany and collaborating with one in Berkeley. And it's basically a custom communications protocol between the electronics in the ice and the computers on the surface. It also has to, in addition to digital communications, there's a time transfer procedures that you need to synchronize all these different sensors to 1 nanosecond. So that's also part of that.
Thank you. All right, Julia is up next.
Thank you. First of all, it bugs me a little bit that IceCube is hexagonal, and I just need to get that out. But second, you mentioned some examples of event rates for high energy neutrinos. What kinds of signals do you get from lower energy neutrinos, and at what rates?
Thanks for the questions. Yeah, we just thought that ICE hexagonal cube didn't have as much of a good ring as IceCube did, but thanks. Yeah, it is a hexagonal prism. We can detect, by the way, we can detect neutrinos whether they interact within the instrumented volume or slightly outside of it. So it's not a well contained volume that acts as our actual detector. So yeah, we're optimized for TeV to PeV energy neutrinos, but we can also detect even higher energy ones. And we can also detect even down to the GeV. And that's how we do a lot of our particle physics measurements on neutrino properties themselves. So that's in our standard method of detecting individual neutrino interactions, we can go all the way down to about 1 GeV or a few GeV. This MEV, mega electron volt scale, we can also access. It's just that we cannot detect individual neutrino event interactions that way. The way that we do that is that if a neutrino happened in the galaxy, for example, if a supernova happened in the galaxy, it would produce this bright flash of MEV scale neutrinos, like the one that happened in the Magellanic Cloud in 1987. and it would flood the detector with these low energy MeV scale neutrinos, each of which would make a small flash of Cherenkov light. And that flash would be so small that it would only travel a few meters from the interaction site. But there would be so many of those that occurred simultaneously that we would see an increase, a collective increase in the rate of light detection by all of the sensors simultaneously. And that would be a bright signal that we could actually measure the time series of the neutrino flash from the supernova with good precision.
Next up is Zuri.
Thank you for the talk. I may have a stupid question. So I saw you list a lot of resource where the neutrino can be produced, and you said that they are weakly interacted with the normal matters. So, I mean, there are a lot of sources which can produce neutrino, but they are difficult to destroy. So, at last, I mean, will the universe full of the neutrinos?
Are you saying in the long-term future of the universe, will
Yes,
the neutrinos remain? That's a good question. In the very long term, we think the expanding universe will make signals be kind of dimmer and less easy to detect from, like astrophysics eventually will be impossible, that we won't be able to see neighboring galaxies, for example. But that stretching out should happen the same to photon or neutrino signals. So I guess that's the longest term answer that I would have to that question.
We have the big, if we get the big rip, I don't know if that goes to neutrinos, but definitely you don't have atoms, right? And maybe even nucleons. So, although quarks don't like to be separated. And this proton decay, then, we'll have more neutrinos around for sure.
But if I could add for today, I agree with everything Justin said, but also for now, neutrinos, as far as we know, are the most abundant particle in the universe. So Justin mentioned that there's some created in the Big Bang. That's my respectable science, is to work on that. And those are as far as we know, the most numerous. So we don't know what dark matter is, so I can't say. But aside from that, of the particles we know of, neutrinos are the most abundant particles in the universe. And there's bazillions of them going through you every moment. Yep.
And they're changing their flavors all the time. That's the other amazing thing.
Yes.
All right, well, we can keep taking questions, but we can also transition into more of a general discussion. So if you have questions for either of our speakers, feel free to jump in to make it more of a conversation. But I'll go ahead and turn, actually, let's see who's left.
Yeah, there are a couple of hands. Maybe
yeah, I'll keep taking hands, but feel free to direct your question broadly. So Achint, you can jump in.
Hi, Justin. Thanks a lot for this incredible talk. I had a question not directly related to neutrinos, but to the process itself. So you drill these holes, right, and you extract the essentially the ice which you melt. I was just wondering if the content of this water or this pristine ice is also studied for its composition itself. Like to sense the presence of microorganisms, if there's life at 2,000 meters deep into the ice, or other related stuff.
Yeah. Can you see that graph?
Yeah.
Yeah, so this is actually work. This was a big topic of the group I did my PhD in Berkeley. My advisor was Buford Price, and he's done a lot of interesting long-term work also on kind of at the intersection between geology and geophysics and astrophysics. Also a little bit related to the work that Brian was talking about. And so a group member there, Brian Bay, developed this, basically exactly what you're saying. If we're doing this drilling into this pristine ice, and we know that glaciologists and geophysicists are very interested in the ice as a time capsule for climate and for glaciology, can we measure the ice while we're drilling these holes? And so he developed this device he called a dust logger, and it basically logs the concentration of dust and volcanic ash as a function of depth by shooting a laser beam into the ice and quantifying the backscattered light. And it has really exquisite precision at the millimeter scale. And the great thing is you do this without needing to extract an ice core. And so this is very complementary information to ice cores that are extracted from both near the South Pole as well as around Antarctica. And you can see they provide really well correlated logs of dust versus depth, which can then be used to correlate with time. Time versus depth is an important part of this. You can see it's on the scale of 100,000 years old. And you can see signals from individual volcanic eruptions, for example, that occurred historically. So we do have a very rich collaboration with glaciologists and geophysicists, and that's ongoing today. Even though I mentioned that the ice is very pristine and very clear, it does have these layers of ash and dust. And so understanding that is a really important calibration task for us.
Yeah, I wonder if you can actually detect the supernova dust that Brian was describing, but actually I'll turn it over to Brian to ask a question.
Oh yeah. So anyway, awesome talk, Justin. So forgive me, I can't contain myself. So you showed the cross section for neutrino interaction. So sort of the probability of neutrino interaction. You showed that it grows very much with energy, and then there's this interesting feature right where you put the box. So I didn't know if you wanted to comment on that feature.
Yeah.
Checks in the mail.
Yeah, it almost sounds like a planned question. Thanks, Brian. I have too many backup slides. Let me try to find a relevant slide.
It looks like that would be really cool to detect. Yeah. So,
it would be.
Yeah.
Okay, so look at that peak. So this peak is the cross section versus energy. You see this really broad spike right there. So now here I'm zooming in on that. And instead of just showing all the different neutrino flavors and interaction types separately in one graph, I'm now showing them separately. And so they're different. Some of you have studied fundamental particle interactions. You might be familiar with the different channels through which a neutrino can interact. It includes neutral current, that is the Z boson, as well as charge current, that's the W boson interactions. And you also have to divide it not only by flavor, but also by neutrino versus antineutrino. Now, if an electron antineutrino collides with an electron, they can produce a W boson. And they have to be at the right, if the electron's at rest, if it's an atomic electron in the ice, and the neutrino collides with it, they have to provide enough rest mass energy to produce the rest mass of the W boson. So you can work out that corresponds to a neutrino energy of 6.3 PeV. That's why you get this big resonance spike there. Now we've known about that process since Glashow proposed it decades ago, and I've given homework questions on it for years. But the first time we actually have identified this in data was just published last week. So that was in this paper. You can look up here if you're interested. And here's an illustration of what this event looks like. Basically, we detected an event with about 6 plus or minus 0.7 PeV of deposited energy. That's the highest energy antiparticle ever detected and the highest energy neutrino ever detected.
Could you get direction information on that?
We do, yeah. In the paper, there's an illustration of our contours constraining the direction of it.
Yeah, that's awesome.
Yeah, that's a very interesting, more recent result. So I'm glad that was asked about.
Thanks, Brian.
Maybe I'll jump in with a question and then we can continue with others. Going back to the first talk, can you talk a little bit, Brian, about about what you might speculate happens to a particle from a supernova explosion as it approaches Earth and then travels through our atmosphere and eventually deposits isotopes on the snow? What's that journey like?
Should I stop share, Brian? Do you want to show any?
Yeah, sure. So yeah, that's a great question. So we spent a lot of time thinking about that. And there's more to think about because it's a big journey. So right. So I could tuck your ear off of the various stages. So there's exactly how the iron 60 and we hope other radioactivities are sort of caught up in the supernova blast. and make it to the solar system. And there's a whole story there, particularly to do with how these small particles will be condensed into these micron-sized particles, dust grains. And we got a whole long story about that. Part of the data themselves have sort of led us to have a kind of new way of thinking about supernova dust. But then the stuff makes it to the solar system. And let me find a suitable. So I showed you these movies. So let me try to share my screen. There we go. And so so I showed you. We've got various simulations with various. Can you see that?
Not yet.
Oh, whoops. Because yes. All right, try again. How's that?
There we go.
There we go. All right. So these simulations are all false colored. So we just picked this one because it had the most ominous colors because we were trying to be dramatic about it. So this is a simulation of a supernova at 20 parsecs, which is a little beyond the most disastrous distance, but still bad enough that we think this might be associated with an actual mass extinction. So the idea is the little red dot is where the sun would be, the little circle is 1 AU, that's the Earth's orbit. And so you can see that the solar wind, the nice spherically symmetric stuff coming off the sun, makes it survives out to about 2 AU, so twice the Earth's distance to the sun before it's pushed back by the supernova blast. And so actually the actual gaseous material from the supernova generally doesn't make it all the way to Earth, but these little dust grains, they punch right through. They're like compared to the small atoms in the gas, they're like cannonballs, and they punch right through and slam into the Earth's atmosphere. And there's a whole story there because these grains will be electrically charged, so they'll feel the sun's magnetic field. But the solar wind magnetic field. But the long story short is none of that matters. They're moving so fast that none of that matters, and they just slam into the Earth and they get atomized. But then there's still a longer story, which I won't bore you with all the details, but we had a whole paper on where we really means my graduate student is the one who figured this out, about the radioactive iron rain and how we go from the top of the atmosphere down to the Earth's surface, and then particularly the surface of the water. And then there's a long story about how we get to the bottom of the ocean. And just to give you an idea of the kind of things you have to think about, the iron-bearing dust, if it goes to the open ocean, it turns out the critters that live there are starved for iron because in the middle of the ocean, there's nothing there for them, and they need it to live. And so they love it, so they eat it up. So there's very little dissolved iron in the water, in the top of the water, in the open ocean, because all the critters are desperate for it and they eat it. But actually that's very good for iron processing because it doesn't actually hang out very long, because then they either die or they leave it in other ways. So I'm not kidding. Dead bodies and fish poop are how this stuff makes it to the bottom of the ocean. And it doesn't take long. It's like a few hundred years. So there's no long delay time from the top of the ocean to the bottom. So from start to finish, it's within less than 100 years, we go from the top of the atmosphere to the bottom of the ocean, and then it just stays. But these are all the crazy things you have to think about for this problem.
That's interesting. There's always an unexpected twist. So I'll turn it over to Feng Zheng, who has his hand raised.
Oh, thank you. I have a question for both Justin and Brian. So the neutrinos seems to have very strong penetrating capability. So I wonder if it is possible to use the manually produced neutrino flux as a neutrino beam as media to carry to send message. I mean, if that is possible, you can just talk to a submarine or some robot underground just directly from satellites. Thank you. I just don't know if that is possible.
Yeah, maybe I could start and Brian could elaborate.
Sure, please go ahead, Justin.
Yeah, this is kind of a recurring fun topic, neutrino communications. Obviously, yeah, like you're saying, submarine would be useful. Like there are obvious military applications. It is possible in principle, and it has been done with one accelerator experiment. of course, the challenge is the very low cross section and therefore the very low bit rate. So it can be done, but you achieve a very low bandwidth. That's kind of the current status. I don't know if Brian has more thoughts on it.
No, but you're exactly right. I mean, you know, that's exactly as Justin said. This is a fun thing. You know, neutrino people, you eventually come around. Generally over beers, you talk about things like this. But yeah, the downside, the upside of them being so penetrating, as you say, is that you can go talk to submarines and so forth. But the flip side of that is they generally also penetrate the submarine. They go right through the submarine itself. So you need a very big detector to detect them. So you know, it's the two-edged sword. But yes, what you say is people have definitely thought about that.
Just,
Awesome.
how did they modulate the beam to carry to transmit message?
One way is, so typically the way you make a neutrino beam is starting with a proton beam and then colliding a target. And one way is that you could just turn on and off that beam or steer it onto and off of the target.
Like a Morse code?
Yeah.
Okay.
Yeah, then there are different interesting ways of how you would choose to encode the signal there. Kind of like our communication method between the surface and the domes.
So we had the neutrino experiment in the water outside of Hawaii, kind of like what you guys did. I don't know if that's still running or if it was a precursor to what you guys are doing. But the submarine could, in principle, could look at the water outside and do what you do, have a much larger volume detector than having something housed in the sub.
Yeah, that was called Dumond, led by John Lerner at the University of Hawaii. And that was really a forerunner of the whole field of neutrino astronomy. And he's still involved in various interesting applications of neutrinos. I mean, both kind of mainstream neutrino physics and neutrino astronomy, but also reactor monitoring, for example.
So I want to jump in and just note that it's 2:30. So if either of our speakers have to run or anybody who has joined us has to run, please, for sure, feel free. But if folks do want to stick around, we do have the class slot booked till 3. We can.
I have a very quick question for Brian, actually. I don't know if you have to run, but very quick.
No, that's okay.
At MIT, we are, of course, close to the AMS experiment, and that is doing spectroscopy on all kinds of ions that are coming in, right? It's on the space station. It's meant to look for new physics, but it's also giving you abundances of all these different kinds of ions that are coming in. It's got great resolution. Is that useful at all for what you're doing? Because some of the particles will come from supernovae. On the other hand, the acceptance is very small, so maybe you just don't get enough statistics.
Yeah, actually, I'm glad perfect question. So so indeed, just recently, another thing I didn't have time to talk about is there was just within the last month a paper from AMS looking exactly at this, at the abundance of cosmic rays. So the same cosmic rays Justin's been talking about, but these are not his very fancy high energy cosmic rays, but these are sort of the blue collar cosmic rays. They're sort of mildly relativistic, lower energy, merely moving near the speed of light, which are where the bulk of the cosmic rays are. But it's very interesting to look at their composition because they're mostly made of protons, but in fact, they're made, as far as we can tell, of all of the elements. And that abundance pattern is trying to tell you something about the source of these cosmic rays. And that's a whole field to measure these. But as exactly as Joe says, AMS is very good at this. And they just had a paper looking at abundances of various heavy elements. And the long story short is they're looking at iron and other species, like I showed you, silicon, some of the main products of supernovae. And the long story short is they were arguing that the data they see suggests you need a recent nearby supernova to boost the iron abundances to the levels that they see. So that absolutely is a part of this story. Because I mentioned we'd already seen in cosmic rays the specific isotope of iron 60, but they just said even the bulk iron suggests that there needs to be a recent nearby supernova to get the abundances to where we see. Great question.
I can jump in too with another question for probably more about IceCube. So one area of interest in my own research is in advanced fibers. And when I see these really long cables, I imagine, well, you said they performed very well, which is very impressive, but I imagine whether there would be some other manufacturing method that would involve extruding a single fiber that contains the detection elements just within the fiber. And what would be some of the key engineering challenges there? I imagine high pressure and cold temperature, for instance, but I'm curious.
Yeah, that's interesting. Actually, my undergrad advisor, Giorgio Grata, was brainstorming some thoughts along those lines, and it's an idea that's come up in various contexts. The mechanical stresses are an obvious challenge. If you had a glass fiber, for example, you need to survive all of that. In the past, we considered fiber optic rather than copper communications, and we're still considering that for future upgrades. So using the fiber optics for communications is still on the table. There are also ideas of using more like sensor elements based on fibers. I guess that's kind of more what you're thinking of.
Yeah.
Wavelength shifting fibers and scintillator for reading out scintillators is a common field in high energy physics that you're probably familiar with. And we also have ideas of doing that, of kind of having wavelength shifting fibers that might be extending out into the ice. Those are kind of a little bit kind of just blue sky ideas at this point, with a little bit of initial testing.
Interesting. So let me ask a quick follow-up there. How much would be involved, for instance, in like, let's say we created some pipeline for people to prototype alternative fiber sensor designs, and we wanted to add just, let's say, a single channel to the ice, drill a single ice bore and put in a single much earlier stage detectors in proximity to the advanced detector. Is that crazy, or
It's not crazy. Yeah. The main thing to think about, the first metric that you want to think about, is the effective area that it has. Basically, these Cherenkov photons are traveling kind of randomly, and you want them to have a high probability of intercepting a sensor surface. So right now, that's the area of the PMTs, which is 10-inch PMTs. So you want to compete with that. And so another idea that's been on the table is filling the entire water column with some liquid scintillator of some kind. So that's, if you can make advantage of that entire water column, that's a much larger collecting area. But there are also obvious environmental impact considerations of that.
Yeah, I definitely think some of these questions about cultural or environmental impact seem to become important in this area of physics detectors deployed in exotic environments.
Yeah. And
anyone?
Yeah, IceCube is subject to the Antarctic Treaty, which is a pretty strict treaty concerning what different nations and different scientific projects do in Antarctica.
So Rob has his hand raised, so I'll let him jump in.
Yeah, I think it follows on from your question, Gianna. But firstly, Brian and Justin, thank you so much. They were both great talks. So question to Justin for the IceCube project. I'd be curious to hear some of the other areas that you'd like to see improved regarding the sensing technology that you use currently. So both in the hardware and the software, what are some areas you'd hope will improve, and thus where we should be focusing our efforts on innovation?
Yeah, thanks. On the hardware, we're kind of limited, like I mentioned, by this relatively small collecting area. We're sampling this huge volume with a relatively small effective sensor area. If you could construct larger sensitive areas while still being subject to these practical constraints of how you get them deep into the ice, that's kind of the main engineering challenge. So there are various ideas of how to improve the PMT sensors themselves, also how to arrange them in multi-channel devices. So we do have a couple stage upgrade of IceCube on the horizon. There's one which is formally called the IceCube upgrade, which is a funded project underway. We're adding 7 new strings with some of these sensor improvement ideas. In the long term, we're looking for a much larger upgrade called IceCube Gen 2, the second generation of IceCube. And so, yeah, we're definitely working on innovating the sensors and open to new ideas as well. If you have multiple channels at the same location, then you can, for example, all surrounding a sphere pointing out in different directions, then you can get kind of like a fly-side configuration. You can get more information from directionality at a single point in space. That's one thing we're working on. So that's on the sensor side, hardware. On software, we are limited by computational bandwidth of the computing that we have at the South Pole, and also the satellite link that we have from there to the North. We're doing, we're generating a lot of data and we're saving basically all of it, but we do have to make some shortcuts in terms of the quality of the data selections and reconstructions and so on that we can run in real time at the South Pole. Real time is really a big deal because we know that a lot of astrophysical phenomena are transient. It might only last seconds to minutes. And so the fastest we can get that information and the most accurately out of the South Pole and onto a public website so other telescopes can point in that direction, the better the science we can do. So computational techniques that can do all these calculations quickly and accurately, including doing it to detect one event in hundreds of billions with that kind of statistical challenge. Those are kind of the software techniques, software challenges. And of course, we're using a lot of machine learning methods and looking for innovation and applying new methods there as well.
So maybe a similar question directed towards Brian for next generation detectors for these supernova grains. I'm curious in particular about in-space detectors. You and I had spoken about, kinematics detection on a skin. You mentioned using the moon as a detector, looking at distributions across the lunar surface. What kind of detectors do you imagine would be suitable for this type? And what do you see as the scientific point of interest?
Yeah, so right, those are great questions. So I think right, I mean you already put your finger on the things that I think are the are the obvious directions to go. I think the moon is probably the most kind of ripe because people are, the Chinese just went to the moon, and as far as I know, this the U.S. plans to return to the moon are still on as we've changed administrations. My impression is that has not gone away. The I guess Artemis mission, I think it's called, as far as I know, is still slated to happen. So there'll be humans landing on the moon near the South Pole, which is very cool by us. And so we put some thought into a little bit into how one might go about exploiting that to look to see if we've got little impacts of supernova dust in the moon, and to collect samples with that in mind to look for. And then indeed, as I showed you, to look at the distribution across the surface of the moon. And then the other thing is again, as you said, that's something that is going to be a harder game. But if you want to, think ambitiously, is since we know that we still have we apparently still have this drizzle of supernova dust, or certainly iron-60 bearing dust that's happening to this day. That's exactly what Antarctica teaches us. That measuring interstellar dust, in situ in space, in interplanetary space would be pretty cool. And there've been some missions that have done that and gotten small amounts of that using like aerogel to stop the dust particles. That's already a hard business, but to be able to do that at kind of larger scale, to collect these things, and so get it to even have a hope of looking at composition and maybe even get arrival directions and velocities, that would be pretty amazing. So I mean, I'm a poor theorist, so I can't I can't even begin to imagine how one does this in practice, but that would be a super cool thing if it could be done.
Cool, interesting. Anyone else? This has been such a lively conversation. I wonder if Justin, Brad, do you guys have questions for each other?
Yeah, so Justin,
Yeah.
for the upgrade to IceCube, I probably should know this, but what's the priority? Is it to more densely pack the hexagon, or do you want to put strings further out to enlarge the sort of the volume that you cover?
Both, of course.
Of course, yeah. I imagine the science, you get different science from those different options, right?
Yeah, so we already have this kind of hierarchical configuration of spacing. I showed mostly the big picture where we have these fairly wide spacing strings, but within that we already have a denser infill, and basically the spacing corresponds to your energy threshold.
Yeah, that's
called deep core, and that's how we access the GeV scale events.
Right.
We're now doing the upgrade. The thing that's formerly called the IceCube upgrade is adding 7 new strings, which is an infill to the infill. So that'll really improve our abilities at this GeV scale, including for neutrino oscillation and neutrino mass measurements.
Nice.
But the other nice thing is our main source of systematic uncertainty, which is very important in limiting most of our analyses, is actually the ice itself, the optical properties of the ice. I mentioned that it's very clear, but it does have these layers of dust. And we're beginning to understand that not only the layers of dust themselves, but actually the ice itself, the crystal structure of the ice, there's actually evidence of birefringence in the ice itself. And so understanding the properties of this naturally occurring detector medium is really important, even for our high energy neutrino astrophysics studies. And so this dense infill also has calibration devices, which will enable us to calibrate those layers and therefore basically recalibrate all of our archival data set, basically reinventing and improving our decade of archival data, including improving our direction reconstruction for the events that we've already detected in the past. And maybe, our ability to correlate neutrino directions with astrophysical sources is related directly to that angular resolution. So by improving the calibration of our archive, we'll be able to improve both our high energy and our low energy science.
It's interesting.
And then in the long term, sorry, just one quick thing.
Oh yeah, go for it.
About the larger spacing, in the long term, IceCube Gen 2 will be focused on even larger spacing than current IceCube in order to get a factor of a few improvement in our sensitivity for a modest cost.
It's interesting that the dust that is a noise source for your experiment is signal for
right.
For
yeah,
as ever thus. Yeah.
So I wonder whether there could be any synergy there, whether it be some kind of this would be very bold given the weak signal, but some kind of in situ detection of the dust grains in the ice itself. Brian had also mentioned ice as a possible future candidate for detection. So something there.
Yeah. I had one for Brian about the biological sediment slide you showed recently. I was thinking also before that when geophysicists want to access timescales beyond ice cores, they go to ocean cores, ocean sediment cores. Is that the direction you're thinking with that? Or
yeah. In fact, I didn't have a chance to say, but or I didn't say much, but yeah. So in addition to these crazy ferromanganese crusts, there now are multiple independent measurements of ocean sediment. So these are, just from ocean drill cores that are just, for geological and commercial reasons, people take these ocean drill cores, and those are available for analysis. And so people have found the iron 60 in there. And the nice thing, and so that's also, the signal's been found. And the nice thing is I remember I said these crazy manganese crusts grow very slowly. So you don't get very good time resolution, but basically don't get any time resolution. But the sediments grow much faster. The signal is more dilute because there's more boring stuff mixed in. But if you can measure it, then you get a time profile. And that turns out to be, I got a whole story that goes along with it. It turns out to be really interesting that the rain on our heads lasted for a million years at least, maybe even 2 or 3. And that's not the first thing you would have guessed, and that has its own implications. So yeah, the sediments are super interesting. And it'd be good to have some more of that.
That might be a wonderful note to close the session. I mean, you guys have been amazing and wonderful to stay on with us so long. It's been such a great discussion. And we'll post the video, so people that couldn't make it are going to definitely enjoy watching it too. But it's been an honor, and it's been wonderful to have you guys come. It's fantastic.
Yeah, thank you so much. And I'll just mention, if you haven't had a chance to peek at the chat, that we had a really diverse audience coming from different universities. Harvard Center for Astrophysics, we had a high school student join. So yeah, I think we got an interesting and very invested crew, judging from the Q&A.
Thank you. It was a fun discussion.
Yeah, it was great fun. Again, thanks again, Joe and Juliana. Really appreciate it.
Thanks a ton, Brian and Justin. Great.